Welcome. We have been discussing radiation for the last two classes, and we started off by learning that it is an electromagnetic wave, and if you are dealing with length scales that are much larger than the wavelength, you did not bother about the fact that it is a wave. We can treat it as rays, and the energy that is carried by a set of rays is quantified using the specific intensity I nu, and we discussed various properties of this specific intensity in the first class. In the second class, in the last class, we discussed what happens when radiation propagates through a medium. So, this is a phenomenological description. We had one term that describes the emission and another term that describes the absorption, and then we found out the general solution and a behavior of that solution, the general behavior of that solution. In today's class, we are going to discuss thermal radiation. So, what is thermal radiation? Thermal radiation is radiation that is emitted from material that is in thermal equilibrium. So, the material is in thermal equilibrium, and radiation is emitted from such a material, then it is called thermal radiation. Now, there is a flaw in the definition itself right at the start, because if a material is in thermal equilibrium, if it radiates, then it is losing some energy, right. So, we assume that the radiation, the energy that is lost is either compensated or it is not significant compared to the energy in the medium. Okay. So, we shall be discussing thermal and the radiation here is emitted from some material which is in thermal equilibrium. So, the material is in that is the material and it is in thermal equilibrium. Okay. And we start our discussion with a specific situation that is called black body radiation. So, right at the start we are going to discuss what is called black body radiation. So, let me first explain what we mean by a black body cavity. This refers, so just imagine a cavity like this, and these are the walls of the cavity, and so the walls enclose a cavity, and there is radiation inside the cavity. So, there is radiation here. And the cavity is assumed to be at a temperature T. We maintain it at a temperature T, and we wait sufficiently long, so that the radiation inside interacts successively with the keeps on interacting with the walls of the cavity, and through repeated interaction the radiation inside comes to equilibrium with the walls of the cavity outside. Okay. So, the radiation inside this cavity is now in thermal equilibrium, it is in equilibrium with the walls of the cavity. Okay. Such radiation that is in equilibrium with material at a temperature T is said to be black body is referred to as a black body radiation. This is a black body cavity. The walls can absorb and emit radiation at all frequencies. That is why it is called a black body. Okay. So, the radiation inside is in thermal equilibrium with this material outside. The material outside is in thermal equilibrium at a temperature T, and the radiation after repeated interaction with the material is also now in thermal equilibrium with the surrounding, with the walls of the cavity. Then this radiation is said to be referred to as black body radiation. So, this is radiation that has come to equilibrium with matter at a temperature T. Okay. Now, what we do is we make a small hole somewhere here, let us say. The hole is just essential for studying the radiation. So, let us imagine that we make a very small hole through which some of the radiation comes out, okay, without disturbing the equilibrium inside. So, the hole we are assuming is so small. So, the amount of radiation that comes out we are assuming is so small that it does not disturb the radiation, the equilibrium inside. Okay. So, this radiation that comes out will have some specific intensity I nu, right. So, this is the specific intensity of the black body radiation. Now, the first thing that we are going to see is that the specific intensity of black body radiation does not depend on the material that makes up the black body, neither does it depend on the shape. So, this does not depend on the material that makes up the walls of the cavity, neither does it depend on the shape or any other property of the cavity. It does not depend. Okay. So, it does not depend on these. Okay. It is independent of all of these things. It depends only on the temperature of the cavity. That is what we are going to see. The only property of the cavity that the specific intensity of this black body radiation depends on is the temperature. So, this is what we are going to see now. And how do you arrive at this conclusion? To arrive at this conclusion, what you do is you consider two cavities. So, let us draw two cavities, two black body cavities. And whose shapes could be different, the material that makes up these two different cavities could be different, and we assume that there is a filter in between which only lets light of a certain frequency nu pass through. So, there are two such cavities, and there are holes in these two cavities which are like this, and the shapes of these two cavities could be different. The materials making up this cavity and this cavity could be different, but they are linked together through a hole like this, and we assume that there is a filter here that only lets light of a particular frequency nu pass through. Okay. Now, the amount of radiation that goes from the left to the right in any specific direction is going to be I nu, and that is the radiation that goes from the left to the right, and the radiation that comes from the right to the left in that same direction, let us say it is specific intensity is I nu prime and the same frequency. Now, if these two things are different, then there would be net energy transfer from one cavity to another, but both the cavities we have assumed to be at the same temperature. This is something I forgot to mention. both the cavities are at the same temperature. So, this radiation is in thermal equilibrium and is at a temperature T, so is this radiation. This is at a temperature T, this too is at a some temperature T. So, if the two specific intensities are different, it would mean that energy would flow from one cavity to another. Now, that would violate the laws of thermodynamics, right. There are two systems at the same temperature, I cannot have heat flowing, energy flowing from one to the other, right, they would be in equilibrium. So, this is not true. So, it essentially tells us that I nu is a universal function, is an universal function of the temperature alone, it cannot be different in these two cavities. Okay. And this universal function of the temperature we denote by B, and this is the Planck function, it is called the Planck function. So, this is an universal function of the temperature, and it is isotropic, we also see from this. Okay. So, the black body radiation specific intensity depends only on the temperature of the cavity, nothing else, and it is isotropic, it is the same in all directions. So, that is one property of the black body radiation which we can arrive at just from pure thermodynamical considerations. Otherwise, it would violate the laws of thermodynamics. Okay. So, that is the first property. Let us now derive another property. This is of the thermal radiation. This is called the Kirchhoff's law. Okay. So, let us again consider a black body cavity. At a temperature T, and let us assume that we have put some material also at some temperature T, at the same temperature T over here. So, this material that we have introduced here is at the same temperature as the cavity and the radiation inside. Okay. And let us write down the radiative transfer equation through this material. So, the radiative transfer equation we see is d I nu d tau is equal to minus I nu plus S nu. Now, note that even though we have introduced this material at a temperature T, it still remains to be a black body cavity, because this is at the same temperature as the rest of the wall. Okay. So, this again is a black body cavity and the incident radiation on the left hand side, we know that it is the Planck function, that it is inside the black body cavity. So, the incident radiation we know is the Planck function. Now, what comes out must also be the Planck function, because this entire thing is still continues to be a black body cavity. So, from this we can say that the source function for this, the source function for this material must be equal to the Planck function, right. If it were more than the Planck function, then the specific intensity would increase when the radiation passed through this, and if it were less, then the specific intensity would decrease. But introducing such a material, this still continues to be a black body cavity. So, the specific intensity cannot change, it must continue to be the Planck function. So, it tells us that the source function for a thermal, this is a thermal medium, thermal, okay, this is at a temperature T. So, for any thermal emission, thermal radiation, for some thermal material, material in thermal equilibrium, this is a material in thermal equilibrium at temperature T, the source function is equal to the Planck function. Or it gives us a relation between the emission coefficient and the absorption coefficient. We have seen that the source function is the ratio of the emission coefficient to the absorption coefficient. So, it tells us that J nu should be equal to alpha nu into B nu T. That is the property of thermal of a thermal material, right. So, what have we learned till now? We have learned essentially two things. So, we have two concepts now. One concept is as follows. Let me just briefly summarize what we have learned. One concept is that of a black body radiation. Let me forget about the hole in the cavity. The black body radiation is a radiation that is in thermal equilibrium. So, this is called black body radiation. The radiation here has come to thermal equilibrium with material at thermal equilibrium at some temperature T, matter at, and we saw that the specific intensity of this radiation is the Planck function, which depends only on temperature, universal, right. That is one thing. The second thing is thermal radiation. Which is different from black body radiation, which could be different. So, thermal radiation, we have some material here which is at a temperature T in thermal equilibrium at a temperature T, could be a gas at temperature T, could be some material, okay, a piece of glass at temperature T, whatever. And radiation that originates from this will have a source function which is B nu, which is the Planck function. But the radiation need not have come to thermal equilibrium with the material. Okay, the source function is the Planck function. The radiation itself need not have come to thermal equilibrium with the material. If it comes to thermal equilibrium with the material, then the radiation also, the specific intensity of the radiation also becomes the Planck function. But this is a more general situation. So, here the source function of the material is the Planck function. Such a radiation is called thermal radiation. Okay. And let me ask you, what is the condition? So, what is the condition that this should, the specific intensity should become equal to the source function? We saw it in the last class when discussing the radiative transfer equation. Recollect? What we had considered this particular problem, right. So, we had considered this particular problem in the last class, where there is radiation propagating through a medium which has the same source function everywhere. The incident radiation could have some specific intensity I nu. As it propagates inside, the specific intensity changes, and inside the material the specific intensity is the source function plus this term. Now, as the optical depth tends to becomes larger and larger, what happens? The specific intensity tends to the source function, okay. And finally, given adequate optical depth, this becomes equal to the source function. So, if this is thermal medium, a thermal material, any radiation that is incident inside on this, provided it propagates for a for an adequate amount of optical depth in this material, it will finally become the, it will come to equilibrium and it will become the Planck function. It will become black body spectrum, basically black body radiation. Okay. That is an important lesson which has to be borne in mind. Right. Now, let us derive a few properties of the black body radiation, of the Planck function essentially, or black body radiation, starting from pure thermodynamic principles. Okay. So, we are going to start from pure we are dealing with black body radiation and we are going to start from thermodynamic principles. So, let me draw the picture again, we are drawing the same picture quite a few times. So, properties. Of the black body radiation, and these are properties that can be derived purely from thermodynamic consideration. So, this is a black body cavity, let me draw it again. At a temperature T. So, there are the walls of the cavity and there is radiation inside, we are dealing with the radiation inside. Now, the radiation inside this cavity can be treated just like any other thermodynamical system, right. It is a thermodynamical system, it is in thermal equilibrium. So, we can treat it just as any other thermodynamical system. And we know from the first law of thermodynamics that the heat that is gained by the system is the internal energy. So, the heat, so if the internal energy goes up, the heat has to either heat has to flow into the system or there has to be work done on the system. That is the first law of thermodynamics. Okay. And we know that this is not a perfect differential, but the entropy, we can write this as T ds, and the entropy is a state function. Okay. So, we can write it, the first law, in this way. Now, for the black body radiation, we have seen what are the properties of the black body radiation that we already know. So, there is one property, okay, a property which I should have mentioned, but I did not. The fact that this radiation is isotropic, for any radiation we saw that the energy, let me do it here, the for any radiation the pressure, we saw the pressure is equal to the internal the energy density of the radiation divided by 3. Right, we have seen this right in the beginning in the first class lecture on radiation. The pressure of the radiation is the energy density divided by 3. Okay. So, the total and internal energy of the system, we can write the internal energy density into the volume of the system, and the pressure we can write as 1/3 the internal energy density. This we have derived in the first lecture, and this we are writing the total internal energy in terms of the density into the volume. So, using this we see that the differential of the entropy is 1 by the temperature into then we have two terms that come from this. The internal energy can go up due to two reasons. One is if the density of internal energy goes up. So, I could have V du plus u dV plus the entropy could also increase due to this increase in the volume and the pressure acting on that. So, that will be u by 3 dV. Right. Another thing that I should mention, so there are two things that I should mention. The second thing is that the total internal energy density, the total internal energy density, so the energy density of radiation is equal to, this also we have derived, it is equal to the integral of the specific intensity over all solid angle, all directions. This we have to divide by C. Right. And so, here since the black body radiation it is isotropic. So, we know that this is equal to 4 pi by C into B nu T, right. The specific intensity of black body radiation, for black body radiation this is the Planck function. So, we know that we have this relation. So, what we see is that the pressure and the energy density of this Planck of this black body radiation both depend only on the temperature. So, both of these, so the internal energy, the energy density here U is just a function of temperature alone. The pressure too is just a function of temperature alone. Okay. All of these things depend only on the temperature. So, from this we can write this as 1 by T right. Now, the entropy we know is a function of we can write the entropy as a function of any two of the variables P V and T. So, we write it as a function of V and T right. So, from this what we have is that the derivative of the entropy with respect to temperature at a fixed volume, derivative of the entropy with respect to the temperature at a fixed volume, you can read off now, that is V by u T into du dt. Similarly, the derivative of the entropy with respect to volume at a fixed temperature is 4/3 u. Now, if I differentiate this with respect to V and if I differentiate this at a fixed temperature, if I differentiate this with respect to T at a fixed volume, then the resultant should be equal, right, because the resultant then should be del square S del T del V. So, we are going to differentiate this with respect to V, and if I differentiate this with respect to V at a fixed temperature, what I get is that this is equal to 1 by T du dt. Oh sorry, there this should be 4/3 u by t. And we are going to differentiate this with respect to temperature. So, it should be equal, right. The order of the derivative does not matter. So, if I differentiate this with respect to volume, it should be equal to this differentiated with respect to temperature. And what we have if I differentiate this with respect to temperature is minus 4/3 u by t square plus 4/3 1 by t du dt. Okay. So, we can combine these two terms, take this onto the left hand side, and what we have is that no, not these two terms, sorry, these two terms. We can combine these two terms, take this onto the left hand side, and what we have then is that du dt is equal to 4 times u by t, right. We have just taken this onto the left hand side. So, 1/3 just remains, and here I have 4/3, both pick up minus sign. So, the 3 cancels out. What we are left with is this, which tells us that u, the energy density, is proportional to t to the power 4, right. The energy density of this radiation, of this black body radiation, is proportional to the temperature to the power 4 from purely thermodynamic considerations. Okay. And so this is called the Stefan-Boltzmann law basically. Well, this is not exactly what is referred to as Stefan-Boltzmann's law, but we can derive it. I will just show you how to derive it just now. So, let us write this internal energy, the energy density of this radiation, as AB t to the power 4, where AB is a constant, the constant of proportionality. That is the Stefan's constant, whose value we cannot determine from these arguments. Okay, it just tells us that the energy density is proportional to t to the power 4, right. It also tells us, so once you know the energy density, you know this, so you can work out what this is going to be. So, this will be, no, this is u, this is not the pressure. Okay. So, the u is equal to this, the energy density is equal to this 4 pi by c, the pressure is 1/3 u. Okay. So, what it tells us is that the specific intensity or the brightness, the frequency will not be there, this will not be there, it is integrated over all frequency, right. So, there is a frequency integral here also. So, what it tells us is that the integrated brightness, the integrated brightness is, or specific intensity is equal to C u by 4 pi. Okay. So, this is the specific intensity of this totally integrated over all frequencies of this radiation, that is of this black body radiation. Here we have not the specific intensity, the intensity, okay, integrated over all frequencies. Now, we had also, remember, considered a problem where we had a spherical surface emitting in isotropically in all directions, with the brightness B, and we had calculated the flux at different distances from this, and we had seen that at the surface the flux was equal to pi into B, and that is easy to understand. You have to just integrate over half basically. Okay. So, this was what we had seen, that the flux is equal to pi into B. So, the flux is equal to C times U by 4. So, this is another, this is actually what is called the Stefan-Boltzmann law. The flux of radiation from any surface, the surface of a black body at a temperature T is equal to sigma T to the power 4, where this sigma is equal to C A B by 4, and this is called the Stefan-Boltzmann constant, and this is referred to often as the Stefan's constant. Okay. But the values of these constants cannot be determined from these thermodynamic arguments. Okay. What we can determine is the fact that the radiation behaves like this, and you can then do experiments and determine the value of these constants from the thermodynamic, from this thermodynamic approach. Okay. We can also calculate the entropy density. Once you know the total entropy, because once you know the internal energy as a function of temperature, you can also determine the entropy as a function of temperature. Okay. And the entropy density comes out to be, so the total entropy in the system, let me write it, the entropy in the system, I leave it for you as an exercise. The entropy is equal to 4/3 energy density by T into the volume. Okay. The entropy is 4/3 the energy density by the temperature into the volume. So, this is proportional to T cube, right, because it is the energy density by the temperature. So, the entropy goes as T cube and the energy density goes as T4, and the constant for the entropy is this, or if you want the entropy density, then you can just ignore the volume. Okay. So, what have we done till now? Let me briefly recapitulate before we move on to more detailed discussion. So, until now we have first defined what is thermal radiation, what is black body radiation, and then we determined certain properties of the black body radiation. Its specific intensity is a function of temperature alone, it is isotropic. The source function for thermal radiation is the Planck function, which is also the specific intensity of black body radiation, and then we showed that the total energy density of black body radiation is proportional to T to the power 4. Okay. Another one or two more very useful things before we finish. So, let us now consider, so we have, that is what we have shown before we finish this particular topic. Let us now consider the situation where I do some adiabatic transformation on this black body cavity. Okay, let us consider a situation where, suppose I make the cavity expand adiabatically. What do you mean by adiabatically? There is no exchange of heat, dq is 0. So, the entropy is conserved. Okay. If the entropy is conserved, so under adiabatic expansion, the entropy is conserved, and the entropy I just told you, and you can easily verify, is 4/3 U by the temperature, the energy density by the temperature into the volume. So, what it tells us is that T cube into V is a constant. Right, and we also know that okay, so it is convenient to write this relation in terms of the pressure and the volume. Okay. So, this is one relation. It is also convenient quite often to write it in terms of the pressure and the volume. Now, we know that the pressure is U by 3 and we know that this is proportional to T to the power 4. So, we see that this relation can be written as P to the power 3/4 into volume is a constant, or P volume to the power 4/3 is a constant. Okay, this is very convenient. Now, we have something called the adiabatic index, which you have possibly encountered. P V to the power gamma is a constant. So, here the adiabatic index gamma is 4/3. Okay, this is a thermodynamic medium where the adiabatic index is 4/3. Okay. And this is quite a useful thing that we shall be using quite a bit in this course. Okay. So, this more or less completes the macroscopic description of thermodynamic description of radiation. This is as far as you can possibly get. Now, we shall move on to a microscopic description, some brief idea of the microscopic description of the black body radiation and how you can determine these quantities, the Stephan constant AB, which tells you how much is the energy density, or how you can determine sigma, the Stephan Boltzmann constant. Okay. So, for this you require a microscopic description. So, let us briefly look at what some aspects of this. So, we are going to look at this. So, microscopic. So, we are going to let us start off by considering a volume, a cube like this of side L. All three sides are L. Okay. So, a volume is L cube, and we will assume that there are electromagnetic waves inside this cube, and we will assume periodic boundary conditions. Okay. So, if you have periodic boundary conditions, then the waves that you can have, the wave number of the waves that you can have is going to be restricted, right, and it will have to be such that one entire wave fits into this box. So, this is one possibility, or you could have two wavelengths fitting into the box, etc. So, what you can say is that the wave vector for all possible electromagnetic waves inside this can be written as 2 pi by L into, let us say, L I plus m j plus n k, where L, m and n are integers. Okay, so, the possible wave vectors for the electromagnetic waves that you can have inside this box are restricted, and they are of the form that the wave vector should be 2 pi by L, L into I plus m into j plus n into k, where L, m and n are integers. Okay. and the frequency of the angular frequency we know omega is equal to, for electromagnetic waves in vacuum, it is the speed of light into k, or we can straight away write down the frequency which is of interest to us. So, this is going to be C k by 2 pi. So, each such k we are going to refer to it as a mode of the electromagnetic radiation. Okay, so, this is one mode, one set of integers is one mode of the electromagnetic radiation. Okay, so, these are the possible modes of the electromagnetic wave that are allowed inside such a cubic box. Okay. And corresponding frequency is here, and we know that these are photons. So, each mode can have number of photons, and the number of photons in each mode we will denote by Nk, that is the occupation number of that mode. Okay, which is the microscopic relatively microscopic thing here. So, this tells us how many photons are there in any particular mode. So, the entire electromagnetic radiation in this box can be decomposed into different modes, and Nk is the occupation number, the number of photons in each mode, and it will be different for each value of k. Okay. Further, the energy associated with any mode, let us call it epsilon k, is equal to h with one photon is h nu, where nu can be calculated for that mode like this, right. So, the way we imagine think of the electromagnetic radiation in this box, the electromagnetic radiation in this box can be decomposed into modes. Each mode will have some number of photons, that is the occupation number given by the occupation number. Each of these photons will have some energy. Okay, so, the total energy of electromagnetic radiation in this box is to be thought of like this. I hope this picture is clear. Now, let us look at the k, the direction k vectors, the k space. Okay. So, this is the moment the wave vector space kx, ky, kz. And let us ask the question, how many modes are there in some volume element delta k x, delta k y, delta k z. In this volume element, how many modes do we have? And it is quite clear that this will be equal to 2 pi by L cube delta L, other way around actually, we want the number. So, we have this relation that delta k x, delta k y, delta k z will be delta L into delta m into delta n, right. If I just increase k x, only this is going to increase. If I just increase k y, only this will increase. If I increase just k z, only this will increase. So, if I want to count the number of modes, I have to take the increase in this into the increase in this into the increase in this. The product will give me the total number of modes, right. So, what I can say is that delta, the number of modes, is going to be, let me write down the number of modes. So, that is going to be so, the number of modes in this volume element in this space of wave vectors that this is the volume element in the space of wave vectors delta k cube, right, it is delta kx, delta ky, delta kz. If I divide this by multiply this by L cube and divide by 2 pi cube, this gives me the number of modes that are there in this volume element in the wave vector space. Okay. That is essentially delta L into delta n into delta m, right. So, this is the number of modes. Now, I want to calculate the number of photons So, I would like to calculate the number of photons in this range of delta k. How many photons are there in this range of delta k? Okay. So, what I have to do is I have to multiply this with the occupation number of the modes that are there in that volume. And if I want to calculate the energy, the total energy of the photons, the modes that are there in this volume of d cube k, then I have to multiply it with another factor of epsilon k, the energy of each photon, right. So, epsilon k. This gives me the energy of this is the energy contained in the photons that lie in that region of the k space. Okay. And we are interested in the energy density of the photons that lie in that region of k space. So, if you are interested in the energy density, then what you have to do is you can just divide by this L cube, okay, and the energy density of photons that have that lie in that region of k space, you can write now as let me write it here. So, delta E, delta let us say u k is equal to the energy density, that is equal to n k, that is the occupation number, the energy we know. So, let me write it here. So, it is the energy into the occupation number of those modes into the volume occupied cube by 2 pi cube. Okay. Right. Now, it is convenient to work in spherical polar coordinates. So, think of these wave vectors. These wave vectors in spherical polar coordinate I can write in terms of the solid angle subtended by these wave vectors d omega into k square d k. So, I can write this delta k cube as k square d k. The energy of each photon I can write as h nu. I have the occupation number divided by 2 pi cube into d omega, the solid angle. Right. So, the wave vectors I have written in terms of the magnitude and direction, and the direction I have decomposed into solid angle like this. Okay. Now, we want to write everything in terms of frequency. So, let me write it in terms of frequency. In terms of frequency, so I can replace k by 2 pi nu by c. So, the k can be replaced by 2 pi nu by c. So, if I do that, I will have 2 pi cube coming from this. So, that is gone, and so this will become the occupation number into h nu cube d nu d omega by c cube. Okay. So, what have we calculated? We have calculated the energy density of the radiation that is propagating in this small in this frequency interval d nu, that is propagating in this per unit volume, that is energy density that is propagating in this range of directions d omega and in the frequency interval d nu. So, from here we can straight away identify that the we had defined this specific energy density omega, remember this is equal to and the specific intensity I nu is equal to, so you have to just multiply it with C. So, the specific intensity is going to be h nu cube by C square n k. Okay. Right. So, we have seen this is essentially the relation between the specific intensity and the photon occupation number. Okay. This relates the number of photons that are propagating in a certain direction with a certain wave vector to the specific intensity in that of the light of the ray in that direction with the corresponding frequency. Okay. So, this is the specific intensity of the light in the same direction as this wave vector, the same frequency corresponding to this wave vector, they are related like this. Okay. And you can put in a factor of 2 to account for 2 polarizations if you wish, assuming that the light is not polarized. Okay. So, let me stop over here for today and we shall continue on this microscopic approach and see how we can derive properties of the black body radiation from this.